Welcome back to multivariate calculus. In this video, we're going to be looking at generalized coordinates. There are several different schools of thought among educators on how to introduce generalized coordinates or how to approach them in a classroom setting. The true nature of generalized coordinates is something that's a little bit advanced in mathematical analysis, and so we have to simplify it in one way or another. I like looking at generalized coordinates by thinking about parametric surfaces and thinking about reparameterizations. Let me get my head out of the way and show you what I mean. If we have a surface z equals f of x and y, then we can parameterize that surface as r, a function of u and v, with components u, v, f of u and v. That's the simplest parameterization that exists. But it's not the only option. In general, if I want to parameterize this, I can make my x-coordinate any function of u and v I would like. And I can make my y-coordinate any function of u and v I would like. And it still gives me a parameterization, assuming that my function x of u and v and my function y of u and v are picked to give me the spread of values that I need in order to cover my entire surface. If we set it up correctly, we can do this for any change in variables, u and v. And thinking about an area integral over a region in the xy plane, f of x and y dA. Well, when I'm thinking about an area integral, I have my surface up here in space, but the region that I'm integrating is down here on the xy plane. This is what I'm reparameterizing. The xy plane is the surface z equals 0. So I can think of this integral as the integral over a domain of f of u and v and y of u and v ds, where my surface here is the function x of u and v, y of u and v, and 0. Right? By creating a new surface that falls into the xy plane, what I have done is changed my coordinates. And the idea of change of coordinates, the value of change of coordinates, is something that you more likely came across in a previous physics course than you have in a mathematics course that you've taken up until this point. But when you're looking at things and analyzing things geometrically, if you can choose coordinates that you can follow on nice patterns, then using those coordinates instead of the coordinates that you've preset can make your life an awful lot easier. We have done that to some extent already. We have taken our x and y coordinates, and we've reset them in terms of r and theta. And one of the things that I want to do with this idea of change of coordinates is look at that change to r and theta. But there's no reason that that is the tool we wanted to use or the tool that we have to use. For example, we could use curves xy equals 1, xy equals 2, and xy equals 3. We could use curves that have that the natural log of x is 1 and the natural log of x is 2 and so on. And we can use those as a new coordinate system. And thinking about this as thinking about a rippled surface that we're looking down on, right? So these curved coordinates don't make a lot of sense. But if you think about it in terms of take a hillside and divide the hillside up into equal lengths and then look down on the top of the hill, you will see that the lengths end up in very curved orientations. They don't become straight lines. That's what we're trying to do here. And that's why I like building this off of the idea of parametric surfaces. We're taking our weird surface, we're finding coordinates that fit nicely on the surface, and then we're trying to flatten that surface out and make it fit into the xy plane. And we end up with some weird curvy looking coordinate axes, but they're still coordinate axes and they still work. All right, now let's see if we can figure out how they work. And how they work is just a matter of figuring out what ds is. All right, so we need a ds. We have our surface here, and we've seen in previous videos that ds is the magnitude of partial r partial u cross with partial r partial v dv du. And here we have that r of u and v has components x of u and v, y of u and v, and 0. That 0 is really nice. It's going to give us a nice way of simplifying things. Because partial r partial u is going to have components partial x partial u, partial y partial u, and 0. And partial r partial v is going to have components partial x partial v, partial y partial v, and 0. And then when we take the cross product, partial r partial u cross with partial r partial v. Because of those zeros in this column, in the I direction, I'm going to have something times 0, something times 0, something else times 0. In the j direction, I'm going to have something times 0, something else times 0. And it's only in the k direction where something interesting happens. And so calculating the magnitude of this cross product, because there is only one non-zero component, the magnitude is that component. You can go through and think through this whole process every time if you want to. There's nothing wrong with that. It certainly works. But a mathematician studied this idea pretty extensively. Paul, I blank on his first name now. Give me a second as I look it up. Carl Jacobi. Um, Carl Jacobi, who devoted his life to calculating the circumference of an ellipse, convinced that there was a nice, neat formula for it, eventually proved that there was no nice formula for the circumference of an ellipse. But along the way, he came up with a couple of really nice things. One of them is a simple mnemonic for remembering how to deal with this change of variables. The nice thing about his mnemonic is that it will extend very nicely into 3 dimensions, as we'll see a couple videos down the line. But he writes a matrix partial of x comma y divided by partial of u comma v. And he calls this the determinant of a matrix, where we take our rows based on what's happening up here, and we take our columns based on what's happening down here. So partial x is the first row, partial y is the second row, partial u is the first column, and partial v is the second column. And you can work through and realize that, yeah, that actually gives us exactly what we came up with before. And again, the nice thing about Jacobi and the Jacobian, the Jacobian sometimes refers to the matrix itself, sometimes it refers to the determinant of the matrix, sometimes it refers to this. No one can quite agree on which thing is the Jacobian, but this process involves the Jacobian. It was invented by Carl Jacobi. And it's a nice way of remembering what's going to happen that extends out if you have more dimensions. So if we need to change x, y, and z to u, v, and w, as we will just a few videos down the line, then we can just extend this out and create a 3 by 3 matrix instead, and everything works exactly the same way. And I said I wanted to lead off with the example of polar coordinates. We know polar coordinates, x equals r cosine theta, y equals r sine theta. And we've seen before that dA should be r, dr, d theta. So we saw from a geometric argument where this r came from. But if I take partial with respect to x and y, and I take partial with respect to r and theta, right? Well, I have partial x with respect to r. I'll have partial x with respect to theta. I'll have partial y with respect to r, and I'll have partial y with respect to theta. And since x is r cosine theta, partial of x with respect to r is cosine theta. Partial of x with respect to theta is negative r sine theta. Partial of y with respect to r is sine theta, and partial of y with respect to theta is r cosine theta. And finding the determinant, main diagonal cosine theta times r cosine theta is going to be r cosine squared theta minus sine theta times minus r sine theta. Minus and minus is plus. We have r, we have sine squared theta, and that Pythagorean identity seems to come up all over the place in these lessons on integration. Cosine squared plus sine squared is 1, so r cosine squared plus r sine squared is r, which is exactly what we said we were going to get. So dx dy is equal to r times dr d theta according to the Jacobian matrix. And again, that's exactly what we saw when we tried to do the same thing analytically. All right, I like going through that example first because you get that sense of how this works for something where we already know the answer, and that really makes life a little bit nicer. Right. For the next example, I want to look at something where we don't already know how this is going to work and see if we can make some sense of it and see why this can be such a useful thing. All right. So I want you to consider this region on the xy plane. We've got 4 curves here. 2 straight lines through the origin, y equals 3x and y equals 1/4 x. And 2 hyperbolas, y equals 1 over x and y equals 4 over x. And if we wanted to set this up using traditional integration with rectangular coordinates, we would have a bit of a mess on our hands. Right? If we try to integrate horizontally first, notice that we've got essentially 3 separate regions. Right? We've got to figure out what's happening with this curve and either of these. And then we've got to figure out what's happening with the second curve down here. We've got a lot of things happening and no nice edges. If we try to do vertical first, the same thing happens. We've got mixing of a couple of different top borders and a couple of different lower boundaries, and there's no nice way of dealing with that. But what we do have in our favor, what we have are some patterns in what we're looking at. We've got a couple of straight lines. They're all straight lines through the origin. They all have the form y equals u times x. And we have u running from 1/4 to 3, right? 1/4 and 3 right there. And then the other pattern that we have are equations in the form y equals some constant v divided by x. 1 over x and 4 over x. So we can talk about this for 1 less than or equal to v less than or equal to 4. Right. So there is how I look at this and say, well, what if we did something different? right? Is this actually going to be useful? Well, some of that depends on what function we are integrating, but it looks like it could be promising. And that's really what I'm thinking about right now. It looks like it could be promising. The problem is that we don't have enough information to actually do anything yet. In order to do a change of coordinates, we need x as a function of u and v, and then we need y as a function of u and v. We don't have that, but it's not that difficult to get. So that's my next step. Since these are both solved for y, I can use a direct substitution. If y is equal to u times x and y is equal to v over x, that means that u times x is equal to v over x, ux squared equals v, x squared must be v over u, and then x itself is the square root of v over u. All right, that's not too bad. It's not the most obvious thing, but it works, and sometimes that's what's important. Um, we do have the plus or minus going on when we took the square root, but we can go back and reference our region of integration here. We definitely are looking at a region where x and y are both positive, so I don't have to worry about the negative branch of the square root. Right, but now that I have this value of x, I can go back and I can solve for y. Right? Y is equal to u times x. And x is the square root of v over u. We can bring that u inside the square root and then reduce the fraction to get that y is the square root of u times v. All right. So with this change of coordinates, my integral over this region of f of x and y dA, I've now got a very simple region, right? Those limits on u and v are about as simple as they can get. And it's just a matter of, can I make the function work out? All right, well, dA is going to be the partial with respect to x and y over the partial with respect to u and v, the Jacobian here, times dv du. And so if we can figure out this part, then we've got most of the setup that we need. All right, and we're going to set that up as the determinant of the 2 by 2 matrix, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. All right, and with this formulation, the partial of x with respect to u, that's the messiest of all of this. We've got square root of v, which is constant. We've got u to the negative 1/2. The derivative of u to the negative 1/2 is going to be negative 1/2 times u to the negative 3/2. So we're going to end up with negative 1/2 square root of v over u square root of u. That's u to the negative 3/2, 1 over u square root of u. Partial with respect to v, comparatively, is a lot easier. That's u to the 1/2, so the derivative there is going to be 1/2 times v to the negative 1/2, which is 1 over square root of v. So multiply that by the 1 over square root of u, and we get 1/2 1 over the square root of uv. Partial of y with respect to u is going to be 1/2 square root of v over square root of u. And partial of y with respect to v is going to be 1/2 square root of u divided by square root of v. All right, then figuring out what's happening from here. Conveniently, we've got some square roots that cancel each other out when we multiply across, right? Square root of v top and bottom, square root of u top and bottom. So all told, that's going to be negative 1/4 1 over u. And then we're going to have plus, I'm sorry, we're going to have minus, because it's determinant, always subtract the off diagonal. And we're going to do the same thing here. 1/2 root v over root u, 1/2 1 over root u root v. The root v's are going to cancel each other out. Root u times root u is u, so we're going to end up with 1/4 1 over u. All right, combining some like terms there, we get negative 1 over 2u. So my integral is now the integral. U goes from, make sure I got straight which one is which. U goes from 1/4 to 3. V goes from 1 to 4. And we'll take our function f and we'll evaluate x of u and v. We'll evaluate y of u and v. We'll have our negative 1 over 2u dv du. Right. Again, is this going to make our lives easier? Well, that depends on the function right here. If evaluating this function at these interesting points is relatively simple, then we're going to make our lives a lot easier. If we try evaluating the function at these particular curves and we end up with something really messy, then we did not make our lives a lot easier. Actually going through and doing that evaluation is something we certainly could do. It's not that bad. It's just doing some integration. But I'm really interested in the setup, in the change of variables itself, and getting that far in. So I'm going to end this video without actually completing an integration whatsoever. And I'm going to ask you to do the same sort of setup to a slightly different region of integration. All right. So I would like you to think about the integral over some unnamed regions yet, we'll get to that in a minute, of xy over 1 minus x squared y squared dA, where my region in question is going to be defined like this. I want my curves. X times y is equal to 2. X times y is equal to 5. I want my curves x equals 1 and x equals 5, and the region in between there. All right. So what I want you to do is not necessarily to evaluate this integral, although you're welcome to if you are feeling so inspired. What I want you to do is think about the region of integration and see if you can come up with some nice substitutions to make that a constant region. Once you've come up with those nice substitutions, go ahead and figure out what the limits of integration are going to be and figure out an expression for dA. If you can get that far, I'm going to be very happy. If you would like to go on from there to actually evaluate the integral, you're welcome to, but I don't necessarily expect you to. All right, see what you can do with that, and I'll see you in the next video.